In this recording, we are going to start talking about what causes motion. First, we start by Newton's first law of motion, the law of inertia, the one we talked about before. Again, it says a moving object will continue moving in a straight line at a constant speed. Recall, we said an alternative to that phraseology would be to say will continue moving at constant velocity. That's when we don't change the direction and don't change the speed, we keep the velocity constant. And the stationary object will remain at rest unless acted upon by an unbalanced force. And remember, we said unbalanced force, we also called it net force, resultant force, and so on. Now, this tells us you don't need a force for an object to keep on moving at constant velocity. That's what Newton's first law says. An object moving at a constant velocity does not need a force to keep on moving at that same constant velocity. Now, here is Newton's second law. What does Newton's second law say? The sum of all external forces, we also call it net force, net external force, or resultant external force, or the unbalanced force acting on an object is equal to the mass of the object multiplied by its acceleration. So this is the law that tells us how to change the velocity, that tells us what the origin of an acceleration is. And essentially what it says, we need to have an unbalanced force or a net force to have an acceleration. And how do we get the net force? What's a net force? It is an unbalanced force. And what's an unbalanced force? It is the sum of all forces. The sum can be such that the forces are going to cancel out parts of each other and leave a portion that remains unbalanced. Now, one key new thing here that we didn't talk about before, these forces have to all be external forces to the object we are investigating. Internal forces are not going to affect it much. An example I use quite often with students, and it works pretty well, is to pick up two students that have about the same size, ask them for their weight. Usually I ask guys, they're usually less reticent about sharing that information, or I just volunteer some funny information about their weight when I know that they're about equal in weight. Then I can give funny values. I can say, okay, here is John and Jerry. So I can say John weighs a ton and Jerry weighs a ton. And I asked John if he can lift Jerry. So I asked John if he can lift Jerry. And usually he can come and grab him and lift him a little bit. And that's sufficient. Now, and once we determine that, so we determine that John is capable of lifting a ton. Now the next task, since we know that John can lift a ton, I tell him if he can pull on his shoelaces and lift himself, he can get an A in the course without doing anything anymore. Okay, they all laugh, and we all know that we cannot lift ourselves by pulling on our shoestrings. The argument here, John can lift a ton, but he cannot lift it when it is his own ton. John can exert forces on other objects, but not on itself. Jerry can lift John because he's an external force to John, but John cannot lift John. That applies to all forces. The forces that are going to affect the motion of an object are forces from the outside. Now, for example, if you are inside a car, and this is a very interesting question, anything inside the car is not going to be able to move the car. The only thing that's going to move the car are going to be external forces. And I'm sure that some of you are kind of wondering about this. I hope that some of you are wondering about this. Some of you might say, but it's the engine that gets the car going. The engine helps the process, but it's not the engine that pushes the car forward. I know some of you have either experienced or have seen it happen in front of them, a car being stuck in the mud. Believe me, cars stuck in the mud, they have engines too. And you keep pressing on that pedal, and the wheel is going to spin and spin, but the car goes nowhere. Because in that case, the friction from the road to the tire that's responsible for moving the car forward is not there. There is no friction, there is no external force, so the car is stuck. It does not move forward. Whatever internal forces to the car, due to its engine or the people inside or whatever, are not going to be able to do a thing. It's external forces that are necessary. We'll need to remember to address this with a little bit more detail later on. Now the key here, sum of all external forces is equal to MA, and the sum of all external forces, we call it the net force. Now, another way of looking at this, excuse me, the acceleration is proportional to the net force or inversely proportional to the mass. Remember, I did this. We had sum of the F is equal to MA, divided both sides by M, and we get this. So the acceleration is proportional to the sum of all forces, the net force, or it is proportional or inversely proportional to the mass. Now, the unit for a force is the same as the unit of a mass times the unit of an acceleration. The unit of a mass is the kilogram, acceleration is meters per second squared. Kilogram times meters per second squared, what we have here, we call it the Newton. It is a Newton. That's the unit. Now, example of forces are the weight, its unit is the Newton. All other forces are going to have the same units of Newton. Now, the British system of units uses pound for force. So the equivalent unit in the British system of units is the pound. And 1 Newton is about a quarter pound. Just for guidance, when you hold excuse me, a 1 kilogram brick, it's going to feel like you have 10 newtons on your hand. If you hold a baseball, it's going to feel like you are holding 1 Newton on your hand. Whatever you feel on your hand is about 1 Newton. This is the key thing. Forces along the horizontal result in an acceleration along the horizontal. Okay? Forces along the horizontal affect the horizontal acceleration. Forces along the vertical result in an acceleration along the vertical. Forces along the vertical affect the vertical acceleration. Just to say that some other way, forces along the horizontal do not affect the vertical velocity. And forces along the vertical do not affect the velocity along the horizontal. That's key. In other words, this is my object. If I apply a force this way, all what it's going to affect is motion along this direction. If I apply a force this way, all what it's going to affect is motion along this direction. If I apply these two forces, I'm going to have two motions. This is going to affect this, and this is going to affect this. The motion is going to be the combination of both, but each of the forces is going to affect only the motion along its direction. That's very important.